Hello. Let's use calculus to solve an optimization problem. An oil refinery, labeled R in the figure, is located on the north bank of a straight river that is 2 kilometers wide. The pipeline is to be constructed from the refinery to storage tanks located on the south bank of the river, 6 kilometers east of the refinery. Storage tanks labeled in T. Now the cost of laying pipe is $400,000 per kilometer overland to a point P in the north bank and $800,000 per kilometer under the river to the tanks. To minimize the cost of the pipeline, where should P be located? So okay, R and T need to be connected by a pipe system. Now if the only consideration is distance, you would connect R and T by a straight segment. However, that's going to be entirely underwater, and each kilometer underwater is, as the figure in the problem says, twice as expensive as per kilometer over land. Now, an alternative would be to have it go all the way here, and then from this point across T, uh, that direction. So what this does is it minimizes the amount of, it minimizes the number of kilometers of pipe underwater, but then you might be spending too much on pipes overland. So what if you could make the pipeline as economical as possible ah, by trying to remove this red segment. All right, by having a point P here, an intermediate point, so that from R to P, that's the pipe on land, and from P to T, that's going to be the part of the pipeline that's underwater. So from the figure, the entire setup depends on the location of point P. So let that variable distance be x. And how that's going to help us as far as the cost is concerned is because then from R to P, if that's x kilometers, and it's $400,000 per kilometers overland, then part of the cost, C, which depends on x, the location of P, is equal to 400,000 times x. We still have to add the cost of the pipe system from P to T. So for that, we need to know the length of segment PT in terms of x. We could do that by considering this particular right triangle, one of whose dimensions is 2, the height, the width across the river, the length across the river. And the base of the triangle is part of the 6 kilometers in yellow minus the x kilometers we already have from R to P. So this is going to be 6. If you can see what I'm writing, what I'm trying to write down with my stylus, this is then 6 minus x, which means that the hypotenuse, the length of PT, is the square root of 2 squared, which is 4, plus the square of 6 minus x. So that's the length of PT, and therefore the additional part of the cost is 800,000 per kilometer underwater, and the number of kilometers underwater is that radical. The square root of 4 plus the square of 6 minus x to the second power. What we need to do next is identify the domain. Remember, if according to the extreme value theorem, if your function is continuous, the domain is a closed interval, then you have an absolute maximum and an absolute minimum. Now, let's figure out the domain, the set of possible values of x. It's natural to expect x to be 0 or positive, because if x was negative, that would put point P to the left of R, which goes against what we're trying to do, come up with the least cost. So x has to be greater than or equal to 0. And then on the other hand, x should not exceed 6. I guess you want to avoid this dimension of the right triangle being negative. And actually, if x were to go beyond 6, then that would put point P further to the right of point T, the tanks. And again, that is not a very economical choice. So x is no lower than 0 and no higher than 6. I'd also like to point out that when x is 0, you get to account for one of the extreme situations earlier. If x is 0, so P is on R, then the pipe system is straight from R to T. On the other hand, if x is 6, that's going to put point P across T on the north bank of the river. So you have it. Our domain is the closed interval from 0 to 6. Now, before we proceed and find the critical numbers, I'd like to add in one other bit of simplification because the two terms of c of x have a common factor, 400,000, and when you factor it out, you'd be left with x plus the square root double the square root of 4 plus 6 minus x quantity squared. And if you call this other factor f of x, we see that because c is merely 400,000 times f of x, minimizing f would lead to the minimum value of c. The least value of f when multiplied by 400,000 is the least value of c. The x value that minimizes f is therefore the x value that minimizes c. And so because f is simpler, why don't we just do our calculus on the function f? The domain is still the same, 0, 6. So first derivative, f prime of x. You have 1 plus, so you have 2 there, and then the radical is an expression raised to the power 1/2, so you have 2 in the denominator. Then your exponent becomes negative 1/2, so that just brings the radical to the denominator. 4 plus the square of 6 minus x. The derivative this time of the radicand, so you have 4 doesn't contribute to the derivative, so that's that for multiplication. 2, and then 6 minus x to the first power. The derivative of 6 minus x is negative 1. Don't forget to always look for critical numbers of the second type as well, where the derivative would be undefined. But because the denominator is this, it never becomes 0. In fact, that's a sum of two squares, one of which is positive 4, so that sum will never become 0. So if we're going to look for a critical number, the only hope is to solve this expression when equated to 0. Let's see how we can simplify this. Of course, these twos cancel out, so therefore you have 1. Alright, back to black ink. 1 equal to this fraction. It has a negative sign, so let's bring it to the other side. 2 times 6 minus x equals, and then that square root. Alright, uh, 4 plus the square of 6 minus x. That's equal to 1, so the numerator and denominator are the same. 2 times 6 minus x equals the square root of 4 plus the square of 6 minus x. Some of you would probably have at this point already expanded that square, but try to hold off expansions until you get to the very end. Who knows, you may even be able to survive this without doing any expansions. Well, for now, square roots are evil. Let's get rid of that. Let's square both sides. 4 times the square of 6 minus x equals 4 plus the square of the quantity 6 minus x. That square has repeated twice, so I'm not going to expand that. On the left side, triple. 6 minus x to the second power is 4. Instead of expanding, because x only appears in one place inside that squared thing, why don't we just take the square root of both sides? So you're going to have 6 minus x to the second power is 4/3. Then take the square root, 6 minus x. You have 4/3 when you take the square root, 2 over the square root of 3, but don't forget plus or minus. So therefore you have the following two candidates. Just algebra your way through it. 6 plus or minus 2 over the square root of 3. Two critical numbers, but remember x does not exceed 6, so you only are going to be left with this critical number 6 minus 2 over square root of 3. If you're not sure whether that's still in the interval 0 to 6, then for the doubting Thomases out there, this is approximately 4.85, definitely inside 0 to 6. Now our function is continuous, our function c continues on the closed interval 0 to 6, so we just got to evaluate at 0 and 6 the endpoints, and at our single surviving critical number 6 minus 2 square root of 3. So what I'm going to do is I'm going to write down the exact forms, but for comparison you may need to do an approximation. C of 0 is the following: 1, and then 6, 0, 0, lots of zeros here with the square root of 10. Straightforward calculator work. Approximately 5, and then 0, 5, 9, and then 6, 4, 0. C of 6 is 4, and then again, lots of zeros, 6 of them. And then C at our surviving critical number is 8, 0, 0, 0, 0, 0, so 5 zeros, but with 3 plus the square root of 3, a bit nasty, approximated to the nearest integer, 3, 7, 8, 5, 6, 4, 0. Alrighty, so assuming I did these computations correctly, we're trying to find the least cost. So the absolute minimum is this third figure. The first figure is the absolute maximum, which I just underlined, which occurs when x is equal to 0. And when x is equal to 0, if you go back to the figure, that's when P is coincident with R. So the pipe is going to be entirely underwater. So to minimize the cost, let's make sure we answer the question. So where should point B be located? All right, P should be 6 minus 2 over the square root of 3, which is approximately 4.85 kilometers east of the oil refinery. All right, almost done here. Just finishing up the sentence. All right, so that's where you should place point P. So it's roughly 4.85 kilometers to the east of R to minimize the cost. Yay! Alrighty, that's the answer.